Welcome to SciFlux. Here you get daily coverage of the latest scientific research. Every day, we bring you new research in a clear and simple format so you can stay informed without wasting time. Like the video, subscribe, and leave a comment to stay connected and help this channel grow. And if you want each new research delivered directly to you, join the SciFlux newsletter. First paper explores integrating stable microlasers on silicon, especially for high-temperature operation, has long been a bottleneck for optoelectronics. 3-nitride lasers offer strong performance but typically suffer from thermal instability when integrated on silicon. Researchers solve this by developing InGaN ring microlasers directly on silicon with 6/10 cavities and a nanoscale island structure that improves carrier confinement and reduces energy loss. The devices emit blue light, TAD 400 nanometers, achieve stable lacing up to 100 degree arc, show less than 1 nanometer wavelength shift across that range, and operate efficiently at room temperature with a low lacing threshold. This unlocks robust silicon-integrated microlasers for sensing, data interconnects, and high-temperature optoelectronic applications. High-performance computing is essential for modern STEM research, yet most undergraduates are exposed to it far too late. The Argonne Introduction to HPC Bootcamp addresses this gap with an intensive one-week program that teaches core HPC concepts and practical computational tools early in students' careers. The key innovation isn't just the curriculum, but the creation of a sustainable delivery model. Led largely by professional career interns, the program emphasizes detailed process documentation, reusable templates, standardized evaluations, peer mentor training, and structured data collection to ensure consistent quality year after year. The outcome is clear: broader access to HPC skills, better prepared future researchers, and a more diverse, technically capable STEM pipeline equipped to meet next-generation scientific challenges. Nature has long used water as a powerful actuator, from ancient stone-splitting techniques to plants that change shape while bearing load. Inspired by this, researchers are developing hydromorph biocomposites, HBCs, materials capable of programmable shape change through 4D printing. In this study, the team fabricated 4D printed HBCs using flax-reinforced polylactic acid and rigorously measured their water-driven expansion and force generation, benchmarking performance against spruce wood. By tuning print parameters such as layer height and print angle, they precisely controlled hydro expansion, blocked force, and energy density. The results are decisive. These biocomposites reached energy densities up to 37.1 G Edsietsaners Siemens 3, matching the performance of natural wood. This positions 4D printed HBCs as a credible class of bio-inspired structural actuators, materials that can adapt, transform, and generate force in response to environmental stimuli. Radiocesium contamination, especially from 137 Cs, remains a serious environmental and food safety risk. To address this, researchers developed a polyacrylamide silicon dioxide, PAM-SiO2 composite, and rigorously evaluated it as a cesium adsorbent. The material showed strong, spontaneous, and thermally stable binding of cesium ions, maintaining performance even after high-temperature drying. Importantly, 90% of the captured cesium was recoverable using a simple calcium chloride solution, demonstrating reusability and separation potential at scale. In applied tests, the composite removed over 94% of 137 Cs from simulated radioactive solutions, and about 90% from contaminated milk. These results position PAM-SiO2 as a highly efficient, cost-effective, and thermally robust solution for radiocesium removal from both environmental systems and critical food sources. Next study. This master's dissertation demonstrates how geographic location materially alters structural design and construction costs, with snow load as the decisive factor. Using a steel restaurant building as a real case study, originally designed for Bragança, the research analyzed how the same structure would need to change if built in different regions of Portugal, with varying snow classifications. The structure was fully modeled and dimensioned in robot structural analysis, following Portuguese and European standards, notably NPEN 1991-1-3, which governs snow actions on structures. By applying different regional snow loads, the study quantified changes in structural sizing, steel consumption, and overall cost. The findings confirm that even minor climatic variations can significantly impact beam dimensions, material quantities, and economic viability. The takeaway is strategic. Environmental loads must be considered at the earliest design stage. Ignoring location-specific factors leads either to unnecessary costs or unsafe underdimensioning. This work reinforces the importance of climate-aware structural design for safe, efficient, and economically optimized buildings. This proposal addresses a core challenge in autonomous systems: reliable, self-sufficient power. Many devices, environmental sensors, safety mechanisms, and industrial controls depend on batteries or external power, which can fail or be impractical in remote or dynamic environments. The solution is flow-driven auxiliary mechanisms that harvest energy from natural fluid movements, streams, changing water levels, or coolant flow, reducing or eliminating external power needs. These mechanisms can trigger events, adjust structures, send signals, or generate small-scale electricity for low-power electronics. Their versatility enables applications in autonomous monitoring, self-adjusting irrigation, flood warning systems, and industrial safety controls. By leveraging ambient energy, these mechanisms provide resilient, maintenance-free operation, freeing devices from batteries or grids. This research envisions a future where critical systems operate reliably, powered by the subtle, persistent movements of their environment. This study examines the shift toward a circular economy, CE, in Vietnam's construction industry, a sector critical to growth but also resource-intensive and waste-generating. CE emphasizes resource optimization, waste minimization, and resilience. But widespread adoption requires understanding what motivates companies to embrace reuse, repair, and regeneration over the traditional linear model. Researchers surveyed experts in construction and supply chain management, analyzing the data with exploratory factor analysis in SPSS to identify the key drivers of CE adoption. The study successfully quantified the primary incentives that encourage Vietnamese enterprises to integrate CE principles into their operations. These insights offer actionable guidance for policymakers and business leaders, enabling targeted strategies that foster sustainability while supporting the long-term development of Vietnam's construction sector. This research provides a data-driven roadmap for building a greener, more responsible industry. This paper explores the circular construction process as a solution to the environmental impact of building, where construction and demolition waste is efficiently reused to minimize CO2 emissions, transport needs, and virgin material use. The study focuses on the Circboost pilot project in Norway, which demonstrates large-scale application of these principles. In Sortland Municipality, an old slaughterhouse underwent a full transformation. Researchers conducted pre-demolition environmental mapping and concrete quality assessments, followed by selective demolition to recover materials. The recovered concrete was processed into high-quality recycled aggregates, which, along with other reused components, were used to construct a new museum building, showcasing sustainability without compromising quality or aesthetics. The Circboost pilot serves as a practical blueprint for circular construction, demonstrating both technical feasibility and administrative viability. It provides actionable insights for developers and cities worldwide, illustrating how construction can become regenerative, reduce environmental impact, and advance a sustainable built environment. This paper examines the sustainability challenges of the built environment amid rising urbanization and construction demand, highlighting the urgent need to reduce material and energy consumption, waste, and environmental impact. Key levers for change include improved codes and regulations, financial incentives, research investment, circular economy principles, life cycle assessments, biomimetic design, and advanced modeling and data technologies. Central to this effort is the Globe Consensus, uniting experts from RILAM, IABSA, FIB, CIB, ECCS, IASS, and others to promote sustainable infrastructure practices globally. A major milestone is the FIB Model Code, for concrete structures, approved in 2023, offering a unified design framework for new and existing structures with life cycle sustainability at its core. This code provides a global blueprint for environmentally responsible, durable concrete construction, signaling a shift towards smarter, greener infrastructure that balances structural performance with sustainability. Thanks for watching. If you enjoyed the video, please like, comment, and subscribe. Also, join our newsletter to stay informed with the latest discoveries shaping science and innovation. See you tomorrow with a new round of breakthroughs. Take care.